Example number 8. Force F acts at the end of the angled bracket in the figure. Determine the moment of the force about point O. Okay, so if we want to follow the principle of moment or the Varignon's theorem, so we write this is our F sub y, and this here going to the right is our F sub x. And if we can observe, the perpendicular distances of our two forces is already given, so we can immediately do the calculation. So if we do moment about point O, assuming counterclockwise positive, is equal to force times distance. So following the principle of moment, if you can observe F sub y follows a, what do you call that, a clockwise rotation, but for a clockwise moment rather, and our F sub x follows a counterclockwise moment, right? So because our point is here, and then F sub x is going there, right? And our palm is facing our point, so therefore it creates a counterclockwise moment. So this is positive F sub x times its perpendicular distance, which is 0.2, minus our F sub y follows, which is applied 0.4 meters from our point. Okay, so this is, we substitute our values, F sub x. So take note that our 30-degree angle is measured from the vertical and not from the horizontal. So therefore our F sub x will have 400 sine 30 degrees quantity times 0.2 minus our F sub y is 400 cosine 30 degrees times 0.4. So if we do, let's just calculate them first. Sine 30 is 1/2. So 400 sine 30 is 200 times 0.2. So that's 40 minus 400 cosine 30. That's 346 times 0.4. That's negative 138.5640646. Of course, this is already in Newton meters. If we do the solve the expression, so moment about point O is equal to negative 98.5640646, or we write it in our following its true direction or its true sense. So that is 98.5640646. Sorry, Newton meter clockwise. Okay, now if uh, let us follow the original definition of moment. So just like example a while ago, example number 7, but to provide us some comparison. So okay, so how are we going to do that? So first thing would be we will follow the line of action of our force, which is 400, which is subjected applied 30 degrees from the vertical. So therefore, we follow this one. Yan. And then from there, we will create a line that will bisect, that will pass through point O and will bisect the line of action of our F or our 400. So when I say bisect, meaning perpendicular to our line of action, and it will pass point O. So therefore, I am referring to this perpendicular distance. So this is D. So the measure of our perpendicular distance would be this D. So let us call that as DP, D perpendicular. Now, how are we going to measure that given that we only have 0.4 and 0.2? Now, we will follow this, take this part here. We know that from the point where our F is applied, 0.2 ni siya pababaw, and as well as 0.4 ni siya, right? So if we continue this line of action, we will follow it that we create a line parallel to the line of action of F, and still it passes through point O. So meaning, we'll just continue this black line here. Okay. Next, we know that from this point here to this point, that's 0.4. This point to this point, that's 0.4, right? So what we're going to do would be, we will create another line bisecting the line of action of F and bisecting the line of action, this color black line that is parallel to our line of action, which is color red. And where does it pass through? This point. This point. Okay. So if you can observe, we know this entire distance. Let us use this color blue. We know this one. How do we know? Because from point O to this point, that's 0.4. So we can measure this color blue distance. So if we already know that, and from 0.2, if you can observe also, this part can also be measured, the color green part. Let me zoom in. The color green, because we know that the height of that small triangle is 0.2. So therefore, what is important to know is that 30 degrees man CF with respect to vertical, so it means this angle here is also 30 degrees. And since this is 90, because we are bisecting lines, it means this line here, this angle here is 60 degrees. And since this is 90, it means that this this blue angle here is also 30 degrees. So therefore, if you want to calculate our perpendicular distance, which is the distance of our F, the perpendicular distance of our F to O, we need to subtract the color blue line. So let us use color blue here. So D blue minus D green. That small uh that small length of opposite sides of our 30 degrees in our smaller triangle. Now, to calculate for our DB, we can either use 30 degrees or you can also use 60 degrees here. It's up to you because 30, assign 30, but take note that we are targeting this side here, DB, and this side, DG. Okay. So if we are going to use 30 degrees for our DB, the color blue, take note that DB is, that side is adjacent to our angle 30 degrees. So therefore adjacent, meaning we'll be using cosine. Now, if we stick with our 30 degrees for the smaller green triangle, side DG is opposite to our angle 30 degrees. So therefore we will be using sine. Okay, so it means If we substitute it here, dB is equal to color blue 0.4 cosine 30 minus, let me write dP. Okay, minus color green 0.2 sine 30 degrees. Okay, degrees. So, if we take moment about point O, following the original definition, so that's moment about point O, assuming counterclockwise positive, is equal to force times its perpendicular distance. So this is if we can observe that 400 creates a clockwise rotation about point O. So this becomes negative 400 times the entire measure here, which is entire dp, which is 0.4 cosine 30 degrees minus 0.2 sine 30 degrees, and our moment about point O is equal to, so we should expect that it is 98. So that is 0.4 cosine 30. So that's 0.346410161 minus minus quantity 0.2 sine 30. That's sine 30 is 1/2. So 0.2 times 1/2, that's 0.1. So our answer is 0.246410161 times 400, and that is negative 98.56406 Newton meter. Okay, so we write our final answer in its proper sense. So that is positive 98.56406 Newton meter clockwise. Clockwise. Okay, there you have it.